Hey, welcome back to Calculus. In this first day of section 7.8, we're going to take a look at something called improper integrals. I think it's an interesting topic in and of itself, and it's also going to be an important foundation for our work later on in chapter 11 when we look at infinite series. So what do I want to do today with you guys? There's two types of improper integral. I like to call them type 1 and type 2. The first type we'll look at today is where the interval of integration is not bounded. So that's what classifies this kind of thing. I want to look at lots of examples and get you used to the language that we talk about, whether or not these integrals so-called converge or diverge. Okay, so I'll give the definitions down below. Let's get started. I'm going to kind of just look at it with a motivating example. I've got a function drawn over here. You can see it's y equals 1 over x squared. That function's defined actually for all numbers except for x equals 0, but I've just drawn the graph for positive x. All right. And in particular, I'm looking at the area under that graph. You can see in the picture for x between 1 and, well, a number that isn't specified. It's a constant with respect to x, but I'm going to leave it as a variable, t. And the question is, well, what is the shaded area? What's the area under 1 over x squared between 1 and t? The answer is written here, 1 minus 1 over t. Where did that answer come from? Well, the area is just the integral. What are the limits of integration? Well, the lower limit of integration is 1. The upper limit of integration is this number, t, just leaving it in as an unspecified value, t. And what are we integrating? Well, we're integrating 1 over x squared, which I'm going to write as x to the minus 2, right? 1 over x squared is the same as x to the minus 2 if you use exponential notation. Okay, so the fundamental theorem of calculus says take an antiderivative, add 1 to the exponent, and divide by the new exponent. And then we have to evaluate that from 1 to t. So I'm going to leave the minus sign out front, and I'm plugging in t in for x. You know, t is an unspecified value, but it's still my upper limit of integration. So when I evaluate that at t, I get t to the negative 1, and then I subtract evaluating at 1. All right, that's just a way of writing 1 over t minus 1, and if I distribute my minus sign, well, sure enough, we verified the formula. The area of that thing is exactly 1 minus 1 over t. So if you change t, this is clear in the picture. If you change t, you would change this area. So what is the exact area? Well, it's 1 minus 1 over t, whatever t is. T here is a number, if you like, bigger than or equal to 1, as indicated in the picture. Okay. Got a little sequence of pictures here. I know they're kind of small, but I'm just drawing, well, like the book drew them, 3 different values of t, 2, 3, and 5. And so if we use our formula up there, remember that the area as a function of t was 1 over 1 minus t. So if t is 2, that area is 1 minus 1 half, that is a half. So that's what the picture says, right? 1 minus a third is 2/3. 1 minus a fifth is 4/5. In fact, in this picture over here, we're asking, well, what happens as t gets bigger and bigger and bigger? Choosing t further and further and further out to the right. As t goes to infinity, well, 1 over t goes to 0, so 1 minus it goes to 1. Yeah, this 1 over t part goes to 0 as t goes to infinity. So this area under the curve, that's kind of different than an area that we've ever talked about. It's not bounded. The shaded area under the curve from 1 is without any upper bound is not a finite region in the sense that it continues on forever. Right? The screen is ending right there, but this area under that curve, because the curve 1 over x squared never touches the x-axis, right? This gap is always there. It just gets smaller and smaller. But somehow the area, as you look further and further out, approaches something, and it approaches the number 1. So here's how we're going to kind of write that idea down in symbols. What we just looked at was the integral. I'm just writing down what we wrote above. The integral from 1 to this unspecified value t of 1 over x squared dx. But we're not just looking at that integral by itself. When we were interested in what's happening as t goes further and further to the right. So we took the value of the integral as t goes to infinity. In fact, let me just write the computation down again so it's all on one line. We said that that area is 1 over 1 minus t, and that limit is equal to 1. So this, I'm going to just introduce the notation here. We're going to capture this idea by writing that what we computed was the integral from 1 to infinity of 1 over x squared dx. And my little colon equals here means that I'm making a definition. I'm just saying what I mean by this notation. And I have to do that because when we write integrals, our definition only included up to when the limits of integration were numbers. Infinity is not a number. So this is an infinite or unbounded limit or interval of integration from 1 to infinity. Yeah, it doesn't have a bound in the sense that there's no biggest number in it. So how I'm defining that integral is you take the integral from 1 to t for any number t greater than or equal to 1, and then you take the limit of that as t goes to infinity. And the language that we're going to use here in this case, we're going to say that this integral from 1 to infinity of 1 over x squared dx converges. So the verb converge means that the limit exists, converges to 1. And you can think of it as the area under that curve is equal to 1. It's kind of a neat philosophical idea. I'm going to have to kind of zoom in when I say this, but this region is kind of interesting for, among other reasons, the following. That in some sense, it's an infinite region, the shaded area, I mean. What do I mean by infinite? I mean, I can stay in it if my laser pointer were thinner. I can pick points in this region arbitrarily far away from the origin, and they're still in the region. So in that sense, it's an infinite region. It has no end. But in another sense, it's finite. We just calculated that its area is equal to 1. So it's kind of this perplexing thing. It's both infinite and not infinite. Anyway, it's kind of fun to think about it. Okay, so back to the mathematics. Here's kind of a generic picture of what we just did. I did that for the function 1 over x squared, but more generally, if you take any function that's greater than or equal to 0, eventually, so on the interval from a to infinity, in this picture that looks like this. And for this to make sense, it also, like the picture shows, that the limit as x goes to infinity of that function should be 0. Because if it's not, asking a question about that area of that unbounded region is definitely going to be infinite. So this is something that we should just sort of check. It's drawn in the picture. So it's a tacit assumption I'm going to make. Yeah. So if you compute the area from a to t for some value t that's bigger than or equal to a, and you can get an expression for that area as a function of t, well then by this infinite limit, where this infinite integral, I mean the limit of that thing as t goes to infinity. So that's what the author is defining here. We're saying that the integral from a to infinity is just the limit as t goes to infinity of the area under the graph from a to t. Okay, so you pick a value of t. Maybe I'll just draw one in here permanently. And maybe I could call a of t that area. A of t is the integral from a to t of f of x dx. So if you take the limit of that as t goes to infinity and you get a number, then you say that that's the infinite area under there, the area from a to infinity. So here's what I was trying to spit out there. My tongue is tripping up on me at the end of this day about what these integrals mean. So I hope you can see the font. I'm going to actually blow that up just a little bit more so it's a little bit easier to see. That if you can integrate your function from a to t and get a number for every t that's bigger than or equal to a, then if I write the integral from a to infinity of that function, what I mean is take the limit of that expression as t goes to infinity, okay? And that's what we'll say if the limit exists. And we say it's convergent. I'll scroll out here in a second, but it's convergent if that limit exists. If the limit doesn't exist, it's divergent. Okay, so those divergent is the opposite of convergent. The second thing is just we can do it the other way. You can guess what I mean. The integral from minus infinity to b means integrate from a to b, or L to b, it's written here, L to b, and then take the limit as L goes to minus infinity. So it's the same exact idea, but you take the limit in the other direction. So these things are called improper integrals of type 1. Okay, improper integrals of type 1. are these infinite limits of, integration, infinite intervals of integration. Sorry. Okay, so let's just compute a couple of these things. So I've got the integral from 1 to infinity of 1 over x dx. So our definition says that that's the limit as t goes to infinity of the integral of 1 over t of 1 over x dx. Okay, so that's the limit as t goes to infinity of what's an antiderivative for 1 over x? The logarithm. That's from 1 to t. So that's the limit as t goes to infinity of the logarithm of t minus the logarithm of 1. But you remember that the logarithm of 1 is equal to 0. So this is just the limit as t goes to infinity of the logarithm of t. The logarithm of 1 is equal to 0. And as t goes to infinity, so does its logarithm. Yeah, so this integral in our language, that limit doesn't exist, it's infinity. So the integral from 1 to infinity of 1 over x dx diverges. Okay, that's kind of an interesting thing. If we drew, I don't have a fancy picture, sorry, but if we drew kind of a crude sketch, I mean, of the graph of 1 over x, it looks kind of just like the graph of 1 over x squared. It's got the same general features. So this area, if we're talking about the graph under the curve of 1 over x, not 1 over x squared, this area is infinite. That's what we just calculated. The integral diverged. So that's kind of interesting. The area under 1 over x squared was finite, but 1 over x to the 1 was infinite. So that's kind of leading me to wonder about the following question. All functions 1 over x to the p, if p is a positive number, doesn't have to be a whole number, but it can be it can't be negative, because if it's negative, then x to the p is really not a fraction. But if you take 1 over x to some p, power, p is for power, positive number, I want to know, what about this integral? Well, let's run through our machine again. So what would this mean? This is the limit as t goes to infinity of the integral from 1 to t of, and I'm going to write this as x to the minus p for anti-differentiation purposes. So that's the limit as t goes to infinity. I'm going to add 1 to my exponent, divide by the new exponent. Yeah, and then I need to evaluate that from 1 to t. So that's the limit as t goes to infinity of 1 over, I'm going to write 1 minus p instead of negative p plus 1. And that's a constant, so I'll factor it out, and now I'm plugging in t. So I get t to the minus p plus 1 minus, when I plug in 1, any power of 1 is just 1. This constant, 1 over 1 minus p, doesn't depend on t, so I can pull it through the limit. It's just notational convenience. Right, so I've got the limit as t goes to infinity of what is in this bracket. I'm going to write this as 1 over t to the, right now it's 1 minus p, so I need to write p minus 1. If I put that in the denominator, you change the sign of the exponent. Right, does that make sense? I'm looking at this, that's negative p plus 1. When I write it in the denominator, I have to change the signs of everything there. So it has to be positive p minus 1. Maybe that's a clearer way to say that. Okay, and then, well, what is this limit? Well, it really depends on the size of p. Yeah, so I can't really say. I have to kind of make some cases here. Because if p is a number that's strictly bigger than 1, let's start with that case. If p is a number that's strictly bigger than 1, then p minus 1 is positive. Yeah, p minus 1 is positive. So that means this term in my sum, has a positive exponent. So as t goes to infinity, that term's going to go to 0. In this case, the t is really in the denominator of the fraction. The exponent is positive. Yeah. If that term goes to 0, then what do I end up getting? 1 over 1 minus p times -1. So in that case, the limit is going to be 1 over p minus 1. The order changed because I'm multiplying by -1. Yeah, if p, we already said p is positive. It's always positive. If it's less than or equal to 1, well, first of all, if p equals 1, we answered that up here. This is the case p equals 1, and we know that the thing diverged. So this formula, I actually should have said this. My argument here depends that p is not equal to 1, because that's a different case with the logarithm. So we've treated that case already, but if p is less than 1, then the exact same kind of thing I was looking at, this exponent would be negative. So this term is actually in the numerator, right? When you have a negative exponent, it's really in the numerator. So as t goes to infinity, that term is going to go to infinity. The limit isn't going to exist. dne is just my way of writing does not exist. Okay, so it's infinite. So stop the video and soak that in. But if you summarize all of that, this is what I was trying to get at. I didn't know how much room I was going to have, so I can bring it up closer to our work if you want. That this integral, its convergence or divergence depends on the size of p. And in particular, it converges if p is bigger than 1, and it diverges if p is less than or equal to 1. And the author didn't write it here. Let me do it just to make sure that it is, in every case, I'm assuming p is positive. Okay, so we'll use that later. And in fact, we learned even more. In the case it's convergent, we even know what the value is. Yeah, so this kind of agrees with our, if you let p equal 2, you end up getting 1/2. If you let p equal 3, you end up getting 3/2, and so on. Okay. How about something like this? Everything we've done has been power rule. Let's do a quick example where we don't have the power rule. Here it's an exponential. The definition is the same. The lower limit is not a 1 this time, but that doesn't matter. We're still going to take the limit as t goes to infinity. In this case, it's the integral from 0 to t of e to the minus x. Yeah, so we have to take the antiderivative. The antiderivative of e to the minus x is minus e to the minus x from 0 to t. Now I'm evaluating. I'm going to put my minus sign in front of my limit. By properties of limits, I can do that. And so I'm plugging in t for x, and then I'm subtracting, plugging in 1 for x. Yeah, and as t goes to infinity, this e to the minus t goes to 0. So we end up getting minus 0 minus e to the minus 1, or e to the minus 1, or if you prefer to write it as a fraction, 1 over e. So that integral converges, just to get you used to the language. Converges to 1 over e. If we looked graphically at what we just did, you know that y equals e to the minus x. Looks like that. We started from x equals 0. So we were talking about that region in the plane, the infinite region under the graph of y equals e to the negative x. And we just said that its area, we just calculated its area is 1 over e. Nice. All right, we're almost done. The fifth example is the last one I wanted to do in this video. I know I'm talking fast. I hope you're stopping it and kind of soaking it in. This one, I've got a graph. 1 over 1 plus x squared is its formula. So that's the curve that bounds this region. It's 1 over 1 plus x squared. And the picture says that the area is pi, and I'd like to verify that. But this area it's not finite. It goes from minus infinity all the way to infinity. So we have to say, well, what do you mean by that? So that's what this formula, I'm going to zoom in so you can see it a little bit better. You pause the video and write it down if you want to. The integral from minus infinity to infinity, what do I mean by that? Well, I mean, integrate from minus infinity to somewhere, and then that same place to infinity, and add those together. And if both those integrals on the right converge, then we'll say that the double infinite integral converges. Okay? So you can pick the number a to be any real number, and the answer won't depend on it. So to do this picture up here, what am I going to do? I'm going to say, well, let's pick the number a to be 0. So we'll just integrate from minus infinity to 0 and then 0 to infinity. And if those converge, then together. And by symmetry, actually, we can just do 0 to infinity because clearly this picture is symmetric. So we'll just double our answer in the case that that one integral. So that's how I want to handle this thing. So if we come down here to get some place to work here, we're going to say, well, first of all, the area that we're after is the integral from minus infinity to infinity of the curve. And then what I was just saying above is we're going to treat that like that's minus infinity to 0 plus 0 to infinity. Okay, and now that's true for any function that you're doing this from minus infinity to infinity. But this one, this next step is true because of this symmetry. Because of this symmetry, these two numbers, if they're finite, are equal. Okay, because this is the area on the left, that's the area on the right. So this thing would equal 2 times the integral from 0 to infinity, but that's special. I'm going to emphasize it here because of symmetry. Okay, so that's not true in general. And now that's 2 times the limit as t goes to infinity of the integral from 0 to t, 1 over 1 plus x squared. Sorry about the degenerating handwriting, but I'm just trying to go fast. That's the limit as t goes to infinity. Antiderivative of 1 over 1 plus x squared is, I should have asked you to stop the video, arctangent. All these functions that we know the antiderivative of. So this is 2 times the limit as t goes to infinity of the arctangent of t, inverse tangent of t, arctangent of t, minus the arctangent of 0. Okay, so that's 2. The limit as t goes to infinity of the arctangent of t is pi over 2. The limit as, and the arctangent of 0 is 0. All right, so 2 times pi over 2 is pi. So there you go. We were asked, I'm going to scroll. You can stop this and look at all the details you want, but we were trying to show that the area of this shaded region was pi, and that's exactly what we've done. All right. Hope that was useful, and thanks for listening.